Thank you. Start with, well, good evening. I hope everybody's doing well. So how many people here are aviators, fly full-size airplanes? So we have a few. Okay, excellent. What about any model aviators here, fly model airplanes? I know I have at least one, two, okay. What about have flown model rockets before? How many people? All right, so good. So we have a number of people that have flown rockets before. So with that in mind, let's get started. Just a little bit about myself. This is just some pictures of some of the toys that I have the pleasure of playing with. Go ahead to the next one there. So as George mentioned, I'm a professional pilot by trade. I tell everybody at this point in my life I'm 98% retired, but I still get called to fly trips on occasionally and like to keep my hand in it. Surprisingly, right now, because I fly the Legacy model Falcon jets, and that's a Dassault Falcon 900B, is one of the sets of jets I fly. Because those are older airplanes and the fact that there's such a pilot shortage, you can imagine the pilot shortage and the greater shortage with pilots trained in the older model Falcon jets. But that's one of the airplanes I enjoy. But in addition to that, I fly single engine airplanes and I still do some flight instruction in some jets and in some airplanes as well. Let's start with next slide. As George mentioned, I do fly, I love all kinds of air modeling. Free flight, control line, radio control. This was back in 2017. I was a national champion in precision aerobatics intermediate class. So that's just one of the kinds of model airplanes I fly, but I like to fly scale models and jets and all that kind of good stuff as well. Next. In addition to flying professionally and enjoying model airplanes, I fly model airplanes professionally. So I ran a remote aerial sensing lab at UTD for engineering students, physics students, computer science students, all going for either their masters or their PhDs. This is an airplane that I built with the students at UTD. We were doing some interesting studies with the Princeton University. In this case, we were doing boundary layer studies. In other words, the atmosphere that's basically from about 80 feet up to about 400 feet high, because while we know a lot about our upper atmosphere and a lot about the atmosphere at ground level, there's very little sensing done in that boundary layer. So this was kind of fun. So I get to tell everybody I flew for NASA. So that was kind of fun. It's stretching it, I know. In addition to that, I fly rockets, and that's one of the things that we're going to talk about today. In particular, I enjoy scale rockets. This was back when COVID was rampant, and you can see that's a 3/4 scale AMRAAM air-to-air missile. Next slide. And you can see that that flies as well. Let's see here. Next. So I mentioned that I fly all kinds of airplanes. In my first exposure to ham radio, believe it or not, was flying one of these. I've taken two of these across the North Atlantic and delivered them to one to the UK, one to Spain. Actually, one went to Belgium and one went to Spain. So this is a Cessna 421B. This is a picture that's similar to the second airplane I took across. Both times I flew these airplanes, this side window, storm window, which I'm kind of pointed to right there, you can open up to verify that the airplane's not pressurized. Or just get fresh air in if you're flying it not pressurized. We replaced that with a sheet metal piece of aluminum, had a coax go into that, had an antenna that ran all the way out to my vertical stabilizer, all the way out to my right wingtip, and I had an HF radio just like you might have in your garage so that can communicate with air traffic control on the oceanic crossings. So next slide. So when you enter a Cessna 421, that's not normally the first thing you see. That's a 100-gallon fuel tank. There were two of them in this airplane. We took all the interior out of the airplane. We packed it in the nose luggage compartment, the wing luggage compartments, put two 100-gallon tanks on board the airplane. The reason for this is the first one I delivered in May, so I could do the standard blue spruce route. I could go from Goose Bay to Narsarsuaq at the southern tip of Greenland to Reykjavik in Iceland and hit Europe from there. But this particular airplane we were delivering in early February. In Narsarsuaq is not a place you want to be in Greenland in early February. So the only way to get it across at that time was to put two 100-gallon fuel tanks on board, left from St. John's in Newfoundland and flew nonstop to Santa Maria in the Azores. So that's one of two fuel tanks. Next. So this is from the cockpit looking back. and you can see the second 100-gallon fuel tank sitting there. And why not? Let's just put that HF radio and all the electrical connections right on top of that 100-gallon fuel tank. So that's what we did. Typically, when I fueled the airplane, I'd have all the doors and windows open, leave the airplane sit for 30 minutes so that all the fumes from fueling that airplane could get out before I even dared put the master switch on and started to fire things up.
It was basically a flying gas tank.
It was. With the onboard fuel, I had 435 gallons of avgas available to me, which gave me almost 10 hours of flying time, about 8 hours to Santa Maria and the Azores. And I got a license from the FAA to operate that airplane 35% over the licensed gross weight of the airplane, and we used every bit of it. Next slide. So this is kind of an interesting picture. I like it. You can see where the coax came for my HF radio for that antenna that went all the way up to my vertical stabilizer, all the way out to my right wingtip. I didn't think a whole lot about it till I started getting a little bit of ice on the climb outs and the descents. And when that little antenna started to ice, boy, it would get to jumping around and moving. I was thrilled I didn't lose it. Anybody want to take a guess what this is? That little valve that's on that window? That's a pressure relief valve. So I'm flying a pressurized airplane, but I have fuel tanks in the cabin of that pressurized airplane. So if for some reason I lost cabin pressure, that means that the pressure inside the fuel tanks would be much greater than the pressure in the cabin would cause the fuel tanks to rupture. So, having 200 gallons of avgas on the floor of my airplane was not an option. So that would allow the pressure to equalize. But, that was my first exposure to ham radio, because I literally was using ham radio to communicate with ATC. And it was interesting because I had a little bit of an antenna tuning problem on this flight. So as I'm going to Santa Maria and the Azores, I couldn't tune up the frequencies to talk to Santa Maria. But as I'm getting close to Santa Maria, I could tune up the frequencies to talk to Gander in Newfoundland, and they would relay my messages to the folks in the Azores until I got within VHF communication range. So kind of an interesting trip. And I always enjoy those trips because they pay you a ridiculous amount of money, as they should if you're going to carry 200 gallons in the cabin of the airplane with you. But they're always
Single pilot?
Interesting story. So, yes, but I had a friend of mine call me about a week before this trip and say, hey, I just got my multi-engine rating, and I'd like to get some multi-engine time. And I said, well, how would you like to get, and he's used to flying some very small light twins, and the Cessna 421 is kind of the king of the piston twins, turbocharged, pressurized, wonderful airplane. I love it. And I said, well, how'd you like to get about 25 hours in a Cessna 421? He said, that'd be great. He said, where are we going? And I said, Madrid. And he paused for a second. And he said, he said, Madrid, Texas? No. So, and then the better part of that story, in the story I love, so we landed in Madrid kind of in the middle of the night. We took a second airplane, a Metroliner, years later, and we landed in the middle of the night. Any of you familiar with a Metroliner? It's a long, thin commuter, twin-engine turboprop airplane. Pilots used to refer to it as the death tube. As your passenger, you probably didn't want to know that. But anyway, I took one of these across the North Atlantic. So with us, we had a life raft and 2 immersion suits, and of course our HF equipment. And when I picked this airplane up, they were loading it with a forklift. And I thought that was kind of unusual for an airplane I'm taking across. And this Metroliner, which is a big airplane, was full of, things that said Hewlett-Packard and Sears and Toyota, and if you can think of every consumer good in the world, and it said that we're loading this with the airplane and spares. Okay, spares weren't necessarily airplane spares. So we take this thing across the North Atlantic, and I land, and my buddy's got the life raft on his shoulder, and we're coming through the general aviation gate there in Baja Arenas Airport in Madrid, Spain. And they had what looked like a metal detector, the old metal detectors you'd walk through this arch. So I walk through, and there's a guard there at 2 o'clock in the morning. He's got an automatic weapon on his shoulder. And I walked through, and not thinking I'm tired, I just flew all the way across the North Atlantic. And I don't think anything of it, and I hear this huge bang behind me. I mean, it sounded like a cannon going off. And this guard unholsters his automatic weapon, comes running right at me, and I'm like the deer in the headlights look. I just froze, and he went running right behind me, and I turned around, and my buddy had caught the top of our life raft on this arch and toppled it over. So, this guard screaming at him in Spanish, and about that time our host, the guy I'm delivering the airplane to, who I knew, came in, and he settles things down, and we leave. And the whole time this guards are screaming at my friend. I'm slowly working my way toward the exit. So anyway, when we finally got in the car, my buddy said, "You were going to leave my ass there, weren't you?" And I said, "Look, if we both ended up in jail, nobody could bail you out. If I'm free, I can come get you." All right. So next slide. So I want to start this just by talking a little bit about what's happened over the years in radio control airplanes, and then we'll jump off to other things, being what's happening on the frequency. So early RC, and this is a transmitter from about the mid 60s, involved a very simple device. You had what was basically a wireless transmitter, just you had a wireless telegraph, and you'd key it up, and that would cause a relay to close, and the relay to close would cause a rubber band powered escapement to turn, which would move the rudder on the airplane. So originally these huge transmitters sat on the ground, and you had a button in your hand, and of course as electronics got better, you had this was modern back then, you had something you could actually hold in your hand and push the button. And typically they were on about 27 megahertz, and which everything back then was on 27. So if you were flying your radio control airplane in somebody with a boosted CB keyed up, guess what? Your rudder moved, and it would stay over full till he got done transmitting or you got done transmitting. So from there they also got some ham only frequencies in the 53 megahertz range. Next slide. So step up to the late 60s, early 70s, there were some advancements there. And one of the advancements we were still flying rudder-only airplanes, and basically that's what this is a rudder-only airplane. It's basically a free flight airplane that you could steer with a rudder. It gets a little more beyond that, but I won't go there. But we developed the systems that we're still using single channel, but instead of only sending the tone out when we wanted to displace the rudder. And again, the way that tone worked is you push the button once, that rubber band escapement moved the rudder to the right, let it go, it would center, press it twice real fast, it would skip over the left. So one push to the right, two pushes to the left. We got to a more modern system where we were sending a constant signal, a pulsing signal the whole time. So it was an oscillating signal, and it would send a signal to the receiver and the magnetic actuator that caused the rudder to flop back and forth constantly. But because it was going constantly, it wasn't enough to make the airplane fishtail. The airplane flew pretty straight, but I could now move a control stick. And when I moved the control stick, it would cause it to flop more to one side or flop more to the other, and gave us basically proportional control. It was referred to as pulse proportional. And now we started to get frequencies on the 72 megahertz frequency, so we weren't stuck with the problems with the ham radios. Next slide. But we go into modern times. I can't fly an airplane like that on a system. So that airplane roughly uses 15 different channels to operate flaps, landing gear, brakes, differential motor thrust, the rudders, the elevators. There's just a lot going on there. Retractable landing gear. Next. So the modern day radios, there are a couple things going on. Not only do I have a lot of channels, but I have phenomenal programming capabilities. So to give you an example here, I can move all these things, but those of you who fly full-size airplanes and or model airplanes know as we change speed, we change trim. As we change configuration with the landing gear and the flaps, we change trim. So there are a lot of interesting things that I can do with my transmitter now. For one, I'm flying in modes. So every time I move the aileron or the landing gear or the flaps, I'm changing modes, which means I can adjust the trim in that mode so that I don't have to fight the airplane every time I change configuration. So that's pretty cool. As full-size pilots or model airplane pilots, we know as the airplane slows down, the controls become less sensitive. That's one of the reasons we can tell the airplane's getting slow. But this guy's got a pretty wide speed range. So the trick is to not have the controls too sensitive at high speed, but have plenty of throw at controls at low speed. So not only can I have the trim automatically change as I change speeds, I can also have the control throws change as I change configuration. As I put the flaps down more, I can have the control throws increase automatically to give me more authority when I'm coming into land. So that's one of the interesting things about these radios. Not only that, I can have it talk to me. I can have it, when I put the gear down, it says gear down, flaps up, it says flaps up. It'll tell me what I've selected on my switches. Next slide. So to have that level of programming for something like this is really remarkable. Go ahead to the next slide. Now, you can see that this looks just a little bit more complicated than that other radio that I was showing you. So there's a number of things that this radio does that's really quite remarkable. Not only am I sending out a signal to control my airplane, I'm getting telemetry back. I'm getting all kinds of telemetry back. So just to give you an idea, let's see here, go on to the correct slide. All right, so I'm getting telemetry on signal strength, battery current draw, current used, air temperature, temperature of the engine, level of fuel, system brake pressure, altitude, airspeed, GPS position, engine RPM, fuel flow, a variometer, which tells me about my rate of climb or rate of descent. I'm getting all this back. So you can see that's one of the boards. Oh, go ahead. So that's, well, go ahead back one. So I have a screen there. In a number of things I can do. I can have it change screens as I'm changing modes. So while I'm flying, in just up and flying, I may be interested in how much fuel I have left or how much battery voltage I have left. Go to the next slide. Or, you know, if I'm flying a turbine-powered airplane, how my turbine engine's running, what the fuel level is, and I can have it tell me these things. It can say, hey, you're 85% fuel, and I can tell it how often I want it to do. But now when I switched for landing, I'm switching modes. My interest may be a little bit different. I may be more interested in airspeed than I am how much fuel I have left or what my engine temperature is. I can also set any warning I want that, you know, when I hit a certain level, it's going to give me a warning that one of the airplanes I'm flying right now, small airplane, it'll tell me when I have a 3,000 milliamp battery in it, it says, you know, 1,800 milliamps used. And then when I get to 2,200 milliamps, she gets a little more, you know, warning, you know, you've used 2,200 milliamps. So really some remarkable things. And not only does it tell me these things, not only do I have the live telemetry, it's recording everything on the transmitter. So I can go back at any point in the flight and see, well, what was my engine temperature, or what was my altitude, or what was my airspeed, you know, if I have a problem. So pretty remarkable things in modern day electronics. We've gotten away from the 27, 53, and 72, and these are now operating on 2.4 for a lot of the systems. The system that I just showed you, and one of the reasons I got it, it not only operates on 2.4, but it operates on 900 as well. And the beauty of that is the whole world is operating on 2.4 right now. So if I'm flying in an area where I may be out in an open field, but there's a lot of houses around there, everybody's got a modem in their house. Everybody's running 2.4. And these transmitters only have 100 milliwatt output. So it's not a very strong signal, so it's easy for it to get swamped. So I have the 900 backup. And then the radio tells me if it switched to the backup. So I know that I had a problem on 2.4, and I know that hey, I may want to land because I'm on the 900 backup. So pretty remarkable stuff these days. All right, next slide. So coming from RC to rocketry, and you know, many of you raised your hands or told me that you had flown rockets before. Rocketry has come a long way. So we basically have two classes. There's a number of classes, but I'm not going to get into it. But basically, we have a big split. We have model rocketry, and then we have high-power rocketry. Model rocketry is anything up to 1,500 grams total takeoff weight, roughly 3.3 pounds, or 125 grams of propellant, or a G motor, whichever of those you hit is the limit. So we're going to talk about things. This particular project, I was too close to this when it took off. It was a friend of mine's rocket. That is powered with an O motor, and we're going to talk about that, what that means, an O 25,000. That's roughly a 135-pound rocket at 16 feet tall. You can see just how long that flame is out the bottom. That motor is over 5,600 pounds of thrust. So a little bigger than your Estes rockets that you were flying as younger. Next. Yeah, just, there you go. One more click. All right, so big or small, rocketry hadn't changed that much. I mean, typically we have all the parts and pieces of your rocket, your parachute, your nose cone, your body tube, your fins. We typically have a motor mount in that rocket that as you can see in George's rocket here, that it's roughly 2 inches in diameter, but we have a motor mount that reduces it to the appropriate size for the motor. When we do some really high altitude stuff that I enjoy doing, the body tube is the motor mount. It's referred to as a minimum diameter rocket. I'm going to talk about that a little bit. Next. So typical stages of the flight, we have our ignition and our thrusting. Once the motor stops thrusting, the rocket coasts. And that's where you're getting most of your altitude is actually during the coast. Think of it about like if you shoot a bullet out of a gun. It's accelerated for a very short period of time, but the coast is rather substantial. When we reach apogee at the top, at that point we need to do something to slow the rocket down. And we put out our recovery device, and the rocket floats down under parachute, typical model rocket flight, and we get to do it again and again and again. So I have some rockets that have over 30, 40 flights on them. Next. So rockets are big and small. So these are some very tiny rockets. You can see the quarter right there. Those very small engines, those are 1/8 A engines. And you can see those rockets that fit in the palm of your hand. Those rockets, the larger one on the right probably goes 75, 80 feet. The one on the left would go 120 feet. I actually, I hadn't checked recently, but in 1991, it was about 1993, I set a national record for 1/4 A rocket glider. And to my knowledge, that still stands. So I have held for a long time a national record in rocketry, but for some very, very tiny rocket gliders. Next. So back to rocketry, just generally speaking. So the standard Estes size rocket, this what I'm holding right here is an Estes C motor. And this is 2.75 inches long, 18 millimeters in diameter. And we're going to talk about what a C motor means here just in a minute. But I have 4 motors there that are all C6s. But I have a C60, which we use for staging, a C63, which would be great for George's rocket here, which would send it roughly 300 feet, 350 feet high, a C65 for mid-level, and then a C67, which has a longer delay. And the difference between those is the delay time, the time that it goes from the time that the rocket motor stops burning in coast to the time it's firing a charge out the front to deploy our recovery device. But a C motor in a little model like this Streak can send it 2,000 feet high. And that is a very impressive flight for that little rocket. Matter of fact, that's probably the last time you're going to see that little rocket is when you push the button. Next. All right, go ahead. It's going to take a couple pushes. All right, that's good right there. So this is talking about how model rocket motors work and a little bit about the nomenclature. So our black powder motor, which we have right here, and that's what this is a black powder motor, C motor. You have your clay nozzle in the back, your propellant. The propellant hits the delay charge, that burns and puts out some smoke. It hits a black powder charge up front, which fires mostly out the front end. Yeah, you get a little out the rear end, but mostly out the front to deploy our parachute. Now, this again is a B-class motor. And you can see that it's not full all the way up, where the motor I have in my hand is filled to the very top. So on your Estes motors, basically you're from your half A all the way up to your C motors. It's just a matter of how much propellant they're putting in that same size thing. So now, it's time you all can take a nap because we're going to get educated here. So anytime education's mentioned, people fall asleep. So the 6 in that C motor is telling us the average thrust in newtons, and there's roughly 4.45 newtons in a pound. So it's a little over a pound of thrust is what that average thrust of that C motor is. The fact that it's a C motor is telling me that it's between 5.1 and 10 newton seconds of thrust. So in the best way I can illustrate that is I have the C6 sitting there, and I have at home, I have an E6. And you're thinking, well, one's an E, one's a C, but they're both 6s with the same amount of thrust. That's correct, except the C burns for just a little over a second, and my E burns 4 times that long. So when we talk about how much thrust is developed, and basically a newton second is the amount of energy it takes to accelerate 1 kilogram of mass 1 meter in 1 second. Okay. So that's the short story about what a newton second is. So it's a measure of impulse. How much total impulse does this motor have? Next. So this is a color illustration because, we're getting old. We don't like black and white. We like color. Again, and this is more of a C motor. Notice that this one is pretty full all the way from the bottom to the top. and could be any of the C0, the 6, or the 7. The difference with the 0 is the 0 doesn't have any delay and it doesn't have any black powder charge at the front. We use that for staging, as we'll put two of those together, one on top of each other, and when the propellant wall ruptures at the top, it sends flaming propellant into the one above it, it lights it, and we have a two-stage rocket. Next. So typical C motor flight on this, if I use an A motor, I may get 200 feet, B 500-600 feet, and probably a C motor, that one would go to 1,100 feet. For those of you who built rockets as a kid, this was a model rocket from Centuri, which Estes bought out in like 1974, 75. In that one, I redid it recently, and I redid it because, you know, I built that in the 70s, so it was getting a little long in the tooth there. And I did it in White Sands Missile Range. If you ever walk through White Sands Missile Garden, that's how their Honest John is done. Next. Oh, and by the way, I love classic rockets, you know, rockets that were back from the 60s and 70s. This is an Estes Goblin with a D motor, which would be twice the size of a C. It would go roughly 1,400 feet. Which is, again, a very, very impressive flight. I mentioned these altitudes, and you know, to you they're just numbers, but trust me, 1,400 feet is seriously high up for a small rocket like that. Next. So, talking about some more model rockets. I mentioned staging. You can take a small rocket that's not any really taller than George's here, and make a 3-stage rocket and go to 2,500 feet. And that is a phenomenal flight, and that's going to be very hard to see at that altitude, which brings me into what we use our ham licenses for, because recovering something like that can be very difficult. And then the other ones are showing clusters, and we're going to talk about clustering next. So here's a little rocket, and as you can see, it's a little bigger than the small Estes rockets, but it uses 22 C motors at the same time. So he's got what we refer to as H impulse and C motors. Next. And there it is flying, which is great fun and very impressive. Next. So taking that same concept, this is a rocket I built years ago, and I've flown several times, uses 7 C motors, just like this little motor I have sitting here, except I have it in it, they all light at once, I have it staged to 7 more C motors. So this rocket has 14 C motors in it. It is 7 motors staged to 7 motors. Next. And it's an impressive thing to see fly. And because it's kind of big and kind of heavy, it still goes up to about 2,000, 2,100 feet, which again is very high for something like that. But this rocket's big enough, it's a little easier to see than the small Estes. Yes, sir. So the question was, how do I determine the peak altitude? So there are some wonderful rocketry programs out there. One is RockSim, but one of my favorite, which is a freebie, by the way, is called Open Rocket. And you can load it onto your computer. And you can build your model on a computer to determine how high that rocket's going to fly on any given motor. Now, what I find with Open Rocket, and some people don't like it, but what I love is if you use it right, it's darn near perfect. And I'm going to talk about how close to perfect it is here in a second. But that way I can pick the proper delay for my motors for how high the rocket's going to go, which is important. And I'm going to kind of put a pin in that and talk about why the delay is so important here in just a second, that we get that right. But that's an excellent question. So with that computer software, I can determine, I can enter all the things, the altitude I'm launching from, the temperature, the wind direction, speed, size of the rocket, weight of the rocket, length of my launch rod or guide rail, and enter all that in, and I get some very important information. Peak altitude, what the acceleration is going to be, make sure it's going to be stable, how long it's going to take from motor burnout to deployment, all those good things. You had a question? And so the question was, didn't Estes make a tool that you could determine how high the rocket went? And the answer is yes, and they still do. The problem is that single point trigonometry is not so great, but you get 2 people and you get an azimuth, or 3, but even 2 gets pretty darn accurate. You can accurately get how high the rocket's going to go. But the question that was asked before is, how do I know how? You know, how high I think the rocket's going to go? And that's going to become very important in a second. We're going to talk about that right there. So we talked about black powder motors, and obviously as we want to go larger and higher and faster, that we have tremendous limitations with black powder motors, and as they get larger, they get less reliable. And the reason is that the case will separate from the cardboard on the outside, and the flame will propagate up the side of the cardboard, and it'll overpressure the motor, and things get ugly at that point. So enter composite motors. This motor, by the way it's designed and it works, are just like the solid rocket boosters on the space shuttle or on the SLS. Very, very similar. It's a ammonium perchlorate composite motor. And typically, the motor is hollow in the center. We have, it could be a hole, the hole could be offset, it could be a slot, it could be a star. The various shape of the grain is going to determine the burn characteristics. Basically, this motor, unlike the Estes, which is lit from the bottom, we light it from the top. And the motor basically starts the ignition at the top, but the motor burns from the inside out. The motor itself becomes the insulator, the liner to the case, which is really kind of interesting. And these come in a variety of flavors. So in this case, you can see the nozzle in the back just has a cap. Motor liner goes all the way up front. You can see this would be we refer to as a 3-grain motor. It has 3 separate propellant slugs in it that are stacked one on top of the other. Your delay grain is up here. The huge difference in the delay grain between these motors and the Estes motors, if I have a C67, that's a 7-second delay. That means that propellant delay grain burns for 7 seconds. In the composite motor, if this was a C motor and I have the same C67, and let's just say that the C burned for 2 seconds, then that delay grain is actually a 9-second delay. So the nomenclature is from the time that the motor starts to the motor stops producing thrust is how long the delay grain is, even though the delay grain is burning during that time. But the number that's associated with that is from the end of thrust to deployment. Next. Go ahead, one more. Oh, and then these motors have about 2.5 times the impulse per weight of propellant that you have for black powder. So a similar size black powder or composite motor compared to this black powder could be a D or even an E in a small size, which would take a model like George's on a nice ride. Next. And again, this is just a nice diagram of the same thing. This would be a 2-grain motor. Just you can see the little split in the grain, nozzle at the bottom, the cord in the center, delay grain, and there'd be the black powder charge at the top. Next. So just to put things in perspective, okay? So we talked about C motors, and I'm going to use C motors as my standard unit of measure, roughly 10 Newton seconds of power. Let me just take a look at my notes here. Okay, so this particular motor right here, this is the motor case that you're looking at. The fins are welded straight to the motor case, so there is no body tube per se. The body tube and recovery are going to go on the top of the motor case. This motor is a P-class motor, a P8500, roughly 72,000 Newton seconds of thrust, or the equivalent of 7,200 C motors all going off at the same time. I got a little video of this thing flying later. The motor alone on this is 110 pounds. So you can see that, I'm going from one extreme to the other. So this is a picture of this rocket I have flying right here, and I'm going to talk more about this in a second. On this particular picture, that was on an I-285. It was a relatively low altitude flight, just shy of 2,000 feet to test tracking and electronics before I've flown it on big motors. I have flown it up to about 9,300 feet. In a couple of weeks, I may be trying, pushing a little harder up to about 11,000 feet. Yes, sir. That's a great question. The question is, what kind of clearances do I have to get to fly these things? So you heard me talk about model rockets and high-power rockets. So basically, the FAA refers to the model rockets as a Class 1 rocket. You don't have to have anything to fly those. You just have to make sure that you're not going to interfere with full-size aviation in any way, shape, or form. So you can't go off the end of DFW and pop off your model rockets. But to enter controlled airspace with a Class 2 rocket, as the FAA refers it to, or we like to call it a high-power rocket, you have to get a waivered FAR 101. So you have to fill out some paperwork to the FAA and tell them who you are, where you're going to be, request the airspace, and they'll decide if they approve it. And of course, as we're in the DFW area here, there's not a lot airspace that we can use. But this particular flight was out at Seymour, Texas, about 2.5 hours west of here, and we have a waiver up to 30,000 feet out there. And we use it. I'm going to be going to Argonia, Kansas in 2 weeks. Who's heard of Argonia? Okay, I got one person. So you know why we go to Argonia, Kansas to fly our rockets? There's nothing there. There's nobody, most people go, where are you going? And we have a waiver out there to 50,000 feet. Last time I was out in the Black Rock Desert flying rockets, we had a waiver to 485,000 feet. So it gives you an idea of the capabilities of rockets similar to this one. But in this case, just to show you that guy does fly. It's put up about 4 flights so far. Next. So the propellant that we use in these rockets is very similar to the propellant in the solid rocket boosters of space shuttle, as I mentioned before, but we do make some minor variations to it. So in this case, this rocket, if you notice, has a blue flame. What you see coming up around that is all dirt and dust. It's not smoke. It's almost a smokeless motor, but a large blue flame. Any of you guys maybe recognize the top of that rocket, perhaps from your college years? That's a beer keg. These guys, some people, we all do different things. Some people are into electronics, some people are into tracking, some people build their own motors, some people want to go as high as they possibly can. This group decided that they wanted to shoot a keg of beer up to about 8,000 feet, recover it, put a tap in it, and have their party right there on the plot. But it does show that nice bluish flame. Next. Adding magnesium to the fuel produces what we call a sparky motor and produces quite an effect at the loss of impulse because you're adding mass in the form of magnesium to create this effect. You're losing thrust in the rocket, but puts up a very interesting flight. And these are just a couple of the variations, by no means all the variations. So you're going to see rockets with red flames or green flames or sparky motors or even black smoke. It just depends how we're mixing the propellant. Next. So here's what we want to see at the end of the flight. We want to see a parachute come out. We want to see the rocket come down undershoot. This is your standard model rocket deployment. So the parachute comes out at the top. Hopefully it comes out at the top. So going back to your question before about knowing how high we went, as these rockets get bigger, putting the parachute at the top becomes, or our recovery at the top becomes crucial, because you can imagine at high speed putting a parachute out does ugly things. I've seen parachutes come out at close to Mach 1, and that is very ugly, I'm here to tell you. So even if it's getting most of the way up to the top, if it still has a lot of upward vertical movement and you put out the parachutes, it's going to be very hard on the recovery system. It could rip the parachutes to shreds. It could separate the shock cord. There's a problem. Same thing coming downhill. Once the rocket hits apogee, it starts its way down. And if the rocket gets accelerated too far past apogee and you put out your recovery device, again, you're going to tear things to shreds. So it gets really ugly. So it's important to know, if we're using a motor delay, how high that rocket's going to go and what kind of delay we need to hit the top. But this rocket creates several problems. First, delays vary based on manufacturing standards and outside air temperature. If it's really cold, they may burn a little slower. If it's really hot, they may burn a little faster. Same thing with the age of the propellant. So getting that recovery device out the top, especially with larger rockets, becomes more problematic. The second thing is, I mentioned rockets going to extreme high altitudes before. I've done over 20,000 feet. Some of my friends have done, one rocket that you'll see here has done 140,000 feet. You can imagine putting a parachute out like that at the top. It's not really what you want to do, because they'll go a long way. So next we're going to talk about things. This is kind of a fun picture, but really kind of exacerbates what I'm talking about. That, this is oh God, I want to say that guy weighed like 198 pounds. So putting a big parachute out at an unopportune time would rip something like that to shreds. By the way, that is an upscale of a little rocket about 6 inches. Well, actually, that's a mosquito. Yeah. So this is a little bit bigger version of that. That flew on an N-class motor. So give you an idea. We do some unusually crazy things. Next. And of course, this is what we're trying to see, that the parachute's out, the rocket's recovered in one piece, and we're able to do this again. Next. So how do we get the laundry out at the top? So on my larger rockets, much like this one, I'm not using the motor to get my parachute out. I'm using some electronics. So this little guy on the right is an older version of a flight computer, which uses a barometric sensor that senses the rocket's acceleration and its altitude. And when it senses that the rocket's no longer gaining altitude, it'll fire a charge which will put out a drogue parachute, allow me to come down about 100 feet per second. And then I can program through a series of dip switches what altitude I put out the main. So anywhere from 200 feet up to about 1,200 feet, I can decide what altitude I put the main out, and the main will slow the rocket down to about 20 feet per second for a soft landing. Now, these older altimeters had a couple issues. The first, if the rocket were hit the speed of sound, you get a pressure wave as you go through Mach 1. In the older, less capable programming and the less capable sensors would sense that is a cease in vertical ascent, and it would put the parachute out at Mach 1. And that's how I can tell you I've seen many rockets that didn't like that very well. I mean, you see all kinds of pieces fluttering down out of the sky, because the second that happens, the rocket separates, the parachute comes out, is instantly destroyed, and then as the rocket's put on its side, it puts a bad load on everything, and it just tears the airframe itself to shreds. The second thing with this particular altimeter is that it would only give me peak altitude. So when I got the rocket back, it would give me peak altitude, but that's all the information I got. So what they started to do is this thing had a series of dip switches on it where I can program out, say, okay, I don't want you to do anything for the first 5 seconds. And that's a great idea. So now as I'm transitioning through Mach and it hits that bump in pressure, it's not going to deploy a parachute. The problem is if I have some kind of failure, if the motor spits or quits or does something crazy, for 5 seconds it's not going to do anything. So you have to wait for that to come out. Enter the more modern flight computer, and that's what this is. And as you can see, it's a relatively small device. And I actually have one of those. If after we have the meeting, I can pull that apart and you can see it. What that does is the sensor's better and the programming's better, so it understands Mach transition. It's not going to do anything crazy as I go through the speed of sound. And this is collecting data at the same time. I'm getting data every 1/10 of a second. It's telling me about how high the rocket is. And through that, I can do some really amazing things. So I'm not only just getting peak altitude, but it's telling me about not only my performance on the way up, but my performance on the way down. How did my drogue chute work? How did my parachute work? So this is, and I can pull this apart later and show everybody, this is that center section. There's what we refer to as a switch band. You can see I have a pallet there, and I have my altimeter mounted. And it's probably easier to see in the picture, but you can see next to these silver lines some very small holes. Those are the pedostatic holes that allow the air pressure to enter into the rocket so that the barometric sensor can do its job. Okay, just a little bit next. This is the back side of it. You can see the battery. Notice those 2 tubes that are glued to the pallet. They slide on some all thread that's glued into that section, and you can see a switch there, which is just a very simple switch. It works with a screwdriver. It's nothing but a screw, and there's 2 prongs that come up out of the switch assembly. And as I turn the screw in, it contacts those prongs and gets the altimeter doing its thing. So that's my on-off switch. And then on the side here, and you can see it if I spin the rocket around, and I have it kind of sticking out, you can see a little piece of nylon thread sticking out there. That gets screwed all the way in to be flush with the tube, and that's my axis for my switch that I can turn it on. Next. That's just showing the all thread coming out the bottom. You can see the top of the bulkhead there with a Dean's connector where that goes to an electrical match, which goes to a tube, which holds my pyrotechnic charge to deploy my parachutes. One for the drogue, one for the main. Next. So talking about dual deploy, that drogue and main, this is just a nice kind of diagram how this works. You can see the rocket launches. At the top, we get our separation of the lower section. The drogue comes out, and then as the rocket gets to whatever our pre-programmed altitude is, we get the main coming out next. And this is what it really looks like in flight. Okay, so that's the rocket under full deploy. This would be the lower section with the motor, drogue chute, electronics bay with the compartment for the main chute, and nose cone. So we're using the electronics to deploy our, and the beauty of this is it doesn't matter how low or how high the rocket flies. My flight computer is going to deploy that drogue chute when it hits apogee. And that's the beauty of it. I don't have to worry about how long the motor delay was, or did I get it right in my simulation. because I've seen many rockets destroyed because the ejection charge went off too early or too late. Going back to George's rocket here, so I talked about this briefly before. So, I showed you the picture with the C60, the C63, the C65, and the C67. So on a C60, if I launch this on a C60, the motor would burn out maybe 75 feet in the air, the parachute would come out and rip the rocket to shreds. If I fly it on the C63, because this is a relatively big, heavy rocket, it's going to reach apogee, it's going to put the chute out, and that's probably going to be pretty optimum. C65, it's going to be on the way down. It may rip the chute, may not, but it's going to put some strain on the rocket. And the C67, this thing would be in the dirt before the ejection charge went off. Not all of our rockets are serious projects. So I have a very dear friend of mine who loves sci-fi. He does some really neat sci-fi stuff. And he wanted to build this rocket, but didn't have the credentials to be able to fly something this big. So this was a rocket that we did together. This is a 65-pound, 7-foot-tall version of the Battlestar Galactica Colonial Viper that we flew on an M-class motor. In kind of a funny story, he was very anxious to get this picture with the Hooters girls. But he didn't want, he said, I can't get in that picture. My wife would kill me. So I've been married now coming up on 45 years. And, my approach to my marriage is a little different. So I take this picture and email it off to my wife and say, hey, just want to let you know I'm having a good time at the launch. But the reason I brought this picture and included in this presentation is not so much just to show you I was hanging out with all the Hooter girls, but to look at this and say, okay, if I look at this, unlike the other rockets, this is not a very aerodynamic vehicle by any stretch of the imagination. The front of the nose cone slanted. It's got all kinds of weapons pods and all kinds of pods sticking out. There's not a place where I could expect a clean airflow over this rocket for deployment for a flight computer, which creates a problem because I don't want that flight computer to prematurely or put my laundry out or be delayed. Next. So you can see that guy taking off. I love this picture for a number of reasons. Interesting thing about this particular day when we flew this rocket, we got out to this launch and there were about 2,500 people out there and the wind was howling and I looked at him and said, I don't think we're going to fly this thing today. And he said, well, let's get it ready for flight. And I said, why? And he said, well, we're out here. What do you plan to do? So we did. And it took us about 3.5 hours to get everything loaded and packed and ready for this flight. In about 10 minutes after we got it ready, the wind just stopped. I mean, absolutely stopped. And we grabbed this thing, and it's 65 pounds. And we go running out to the launch pad, and, we don't know if the wind's going to kick back up or not. We get this thing loaded. We send this thing up to about 5,300 feet, which is a very impressive flight for a rocket like that. And the parachute comes out, and we're high-fiving each other, and this thing drifts about 1.5 miles away. And we go out to recover this thing, and we're just, we're excited, we're juiced, we're celebrating. And then we pick the thing up, and we realize that we didn't think this through. We have a 65-pound rocket. Now it doesn't have propellant in it, so now it's still maybe 53, 58 pounds or so, because we burned off about 7 pounds of propellant. We have to carry this back. Wasn't a good plan. But the rocket did put up a dynamite flight. Next. So we needed something else to make this work. Enter a different kind of flight computer. This is known as an RDAS, Rocket Data Acquisition System. This thing uses accelerometers to figure out what the rocket's doing instead of being basically, and it does have a barometric sensor on it, so we can pick whether we do things barometrically, but in this case we programmed it to use the accelerometer data only. So the accelerometer sees the rocket's accelerating and stops moving and leaning over. Not only that, it has accelerometers in all axes, which becomes very important when we look at what did the rocket do? How did the rocket fly? So I can look at things like roll rate and pitch change and all those things during the flight at the data at the end of the flight. So that's one device. Next to the quarter here on the other side is one of my favorite little devices. This is referred to as a MAD, Magnetic Apogee Detector. What it does is it's looking at the magnetic field of the Earth, and when it sees a change in that magnetic field and how it's interacting with that device, it'll deploy a parachute. So it'll do it at nose over. In how far nose over is a function of whether I'm doing east, west, north, south, or whatever, but it waits for nose over. It detects that via magnetically, and it deploys the parachute. Kind of a cool thing. Next. A couple other interesting devices here. This little device on the left side is one of my favorite devices. This is a little product, and it's a kit made by a company called Egg Timer Rocketry, and it's referred to as an apogee. And what it does, it's a barometric sensor in there. Whenever the rocket sees its highest altitude, it fires a charge. So I can take some of my older model rockets, maybe something just a little bigger than this, and outfit it with that apogee, and I always know that the chute's going to come out right at the top, regardless of what motor I fly, regardless of how windy it is and how the rocket weather vanes or whatever. When it reaches peak altitude, it's going to fire that charge, and then it records the max altitude. So it's giving me max altitude. It's firing the thing at apogee. The kit for this little guy is $15. And takes a little time to put together, which is the perfect recovery device for anything coming out with a single chute. Now, the device next to it is one of my second favorite devices. It's a little bit substantially more expensive, but it's the chute release system. What it does is, if you imagine that we take George's rocket here and we shoot this thing to 2,000 feet on one of my composite motors. We put the parachute at the top, it's going to drift 2 miles. But now I have the chute release thing in here, and what it does is it holds the parachute together, so it puts the parachute out, so while the parachute's out, it's not open. The rocket's going to come down 60, 100 feet per second, somewhere in there, and when it gets to a pre-programmed altitude, it releases the parachute, and the parachute opens. Pretty cool device. So for some of my older rockets, to retrofit them with some of that equipment is very good. Next. So we've talked about a little bit about rocket motors. We talked about parachutes and how all that stuff works. But then once the rocket's flown, particularly as we go to those higher altitudes, even if taking a rocket to 2,000 feet, recovery becomes an issue. You know, where'd this thing go? How do I find it? So here are a couple of the devices that we're using. This rocket I have in front of me has this in the nose cone. Again, for those people who are interested, I can take it out and show you that board. That is a GPS tracking that also has telemetry, that also is a flight computer. So not only am I being able to see where the rocket is, I can see how high the rocket is. By seeing how high the rocket is, I can determine what's going on. So I can see it reach max altitude, and if it's falling bizarrely fast, I know that's really bad. I didn't put out a drogue chute. If it's falling at a medium speed, I can tell, well, at least I got the drogue chute out, and then at my pre-programmed altitude, I should see that rate of descent slow down, and I can see that in real time. Now, while this is what I would describe as a basic telemetry device, there are other devices where it's giving you telemetry back down in real time, not only in terms of the altitude, but in terms of the acceleration, as well as roll rate or pitching. It can give you a lot of information about what the rocket's doing in real time. Velocity. From this, you can get velocity, Mach number, all that stuff in real time, which is really nice. And then it helps you find your rocket. Yes, sir. Okay, so we're talking about telemetry, and the question was, when I get all this information back, are we doing anything meaningful? And the answer is an absolute yes. So what it's telling me is, one, did the rocket perform as expected? Okay, if I'm shooting a rocket to 18,000 feet and I went to 15,000 feet, did it perform as expected? I shot a rocket a couple years ago with a friend of mine, and he's expecting to do 17,000 feet. And when we pick these rockets up, they have a beeper going off, and it beeps several digits in code to let us know how the rocket went. So we pick this rocket up, and we get there, and now we're holding it against our ear so we can listen to the code. We hear it start with a 0 or a 1, which is the first digit, and then it kept beeping out the next digit. So the 1 was thousands, tens of thousands. So we hit this 1, so we know we did 10,000 feet. Next number beeps once, beeps twice, beeps 3 times, 4 times, 5 times, 6 times, 7 times, 8 times. His eyes are getting bigger and bigger and bigger. 9 times. Well, then it beeped the 10th time. 10th time is a 0. So instead of going 17,000 feet, he only went 10,000 feet. So that's one of the things we're looking for. If we had a problem, let's say, and I'll show you some video later, there's some rockets that have some issues. Perhaps during the flight, all of a sudden something came loose, okay, and the rocket goes wonky at a given altitude. Having that telemetry down will tell us at what velocity we had the issue. Did we lose a fin? Did the rocket fold in half? Did the parachute device come out prematurely? And with all this data, we can determine what the failure mode was so that we can do it right next time, particularly for my buddies that are trying to go to some ridiculously high altitudes. I have one friend of mine who's actually trying to go in late September. He's going to be out of Black Rock trying to go to 200,000 feet. So it's important that you get this telemetry down because you may not, the rocket may be so high you don't see the failure. Okay, was the roll rate high? Because that may be another problem. Well, unexpected roll for some reason created some issues that caused the rocket to do something bad. So yes, we get a lot of good information back that allows us to rectify issues that allow us to do better in the future, or it's confirming that we did was correct, that it was my simulation correct. I planned to go to 21,000 feet. Did I go to 21,000 feet? So it's accurate.
Do some of your parachutes, when they deploy, do they fire a black powder charge that may have different chemical mixture in it to give you a color so you can see how high it is when that chute deploys? Can you have an idea of where it is, how high it is?
Well, the black powder charge, we're using one kind of black powder. So the short answer is no. But a lot of time when the chute's packed, we'll use some very orange, what we refer to as tracking powder, which is kind of like orange talcum powder, so that it produces an orange ball when the rocket comes out. And I've done that, but the problem with that is it produces a hell of a mess, both in prepping the rocket and recovering the rocket. So you come back from recovering a rocket like that, not only did you get to see your rocket at 15, 16,000 feet, now everybody gets to see you because you're partially covered in orange powder. So in modern times, we don't do that like we used to do in the past prior to having the electronic telemetry that allow us to see it. Okay. Anyway, so we talked about this guy. These two little bit simpler devices, those are Egg Timer, Egg Finder, same company, Egg Timer, Rocketry. They are kits. The one on the left side with the short antenna is the mini. The one on the right is just the regular. Both are giving me GPS information about where my rocket is, where the one in the center is giving me altitude information. Then finally, the one on the side here, and these can be either 70 centimeter or they can be on 900. It just depends how you get the kits, and you know they make them for both people who have ham licenses and those that don't. Yes, sir.
So you've got a rocket up there, and it's got GPS, and it's telling you GPS coordinates. How do you use that on the ground to find where it's rocket?
Okay, so that's a wonderful question. So I'm getting the information back, and the question was asked is, it's giving me GPS coordinates. How am I using that on the ground? So there are 3 different ways to do that. Before I go there, just this little guy is just a regular tracking beacon. That's in the 220 range. I have a little tracking beacon here I can show that's in the 70 centimeter range. That's kind of where I need your help. These guys, where it doesn't give me a location, it's sending out a signal, and hopefully I can home in and find this thing. And these are great for small, just like fox hunting. And as you can see, and I'll bring this out in a second, that would easily fit in George's rocket here. So if we did send it high and far away, it makes it easier to find. But we're still holding on that question. We're putting a pin in that question about how am I using the GPS information. Next. So this is what one of those kits look like. And it's not terribly hard to put together, but there are 2 things that I find out about putting these kits together. It does use surface mount technology to solder it together. So I find out really how good my eyesight is. It's not so good. And how steady my hands are. And I do use what I refer to as geezer goggles. It's a pretty, like a 4 or 5X glasses that I use to put these things together. And I have to be in the right frame of mind, and my wife has to be out of the house. Next. So this is the kind of information I'm getting. So there are basically, as a general rule of thumb, 3 types of tracking systems. So this one's one of the earlier ones that I have. So what you're looking at here, it's giving me a latitude, a longitude, how good my signal strength is on the GPS, and the max altitude that the rocket reached. This was after the rocket had flown. Again, that field is normally filled with what the rocket altitude actually is. And I can enter those coordinates into an app on my iPhone, and it's going to take me to those coordinates. My more advanced box has a GPS in it. So it looks at where the rocket is, it looks where I'm at, and will it's much better because the one handheld device will not only do that, it'll point to it and give me a bearing in a distance to my rocket. So as I'm walking along, I can see that change. Later, you're going to see that the live telemetry, some people have it hooked to their PC, and they're getting live telemetry on Google Maps, and they're literally drawing a line in the sky of where the rocket is and then showing on Google Maps where the rocket landed. So it gets pretty sophisticated. Next. Just to give you an idea, so this is a rocket I flew several years ago. Again, I like scale rockets. This is a 1/2 scale NASA Hyperion launch vehicle. This is powered with an M-class motor. That motor, just looking at my notes here. Yeah, let's see here. 6,268 Newton seconds are the equivalent of over 628 C motors all going off at the same time, just to put things in perspective. The bottom up to about right here is rocket motor. From here to here is space for my drogue chute. From about here to here is space for my main chute, and then inside the nose cone, like this one, is my tracking device. Okay. Next slide. There it is leaving the pad. And you can see that rocket's about 9 foot tall. That's a pretty impressive flame coming out the bottom of that guy. Next. So this is all the things that my flight computer's giving me. In this case, we uploaded it after the rocket landed, but with a live telemetry system, I can get all this in real time. Next. So what am I getting? I'm getting some really good information. Apogee, 21,275 feet. Not bad for a little scale model rocket. By the way, in the Black Rock Desert, you can follow that all the way up to apogee. It's a wonderful thing to see. You go in Kansas in the summertime, sometimes the skies are clear, sometimes they hit a haze layer at 5,000 feet and they're gone. A couple other things that it gave me, velocity. And if you notice, it's showing 1,820 feet per second is my max velocity. But that's a little misleading because of the fact that, you hit a bump at Mach, which is going to throw your data off, so you can see a best fit. So the really is a practical matter if you smooth the data 1,570 feet per second, which turns out to be about Mach 1.51. Pretty impressive. Some other even more important information. Well, how did I do under drogue? So it's telling me my drogue chute. It tells me that the drogue came out and that my average rate of descent was 71.6 feet per second, which is pretty close to that 80 feet per second I was looking for. So my drogue chute was properly sized. And then it told me my main chute, while it was programmed for 1,100 feet, came out, they actually deployed at 1,095 feet, and that my rate of descent was 19.4 feet per second. Again, very close to my 20 feet per second desired rate of descent. Going that high and using that dual deploy method, I recovered this rocket a half mile away from where it took off. So really pretty impressive. So you get that kind of information. Next.
How long was that entire flight? Launch?
Go back a slide. So let's see here. It's on here some, yeah. Well, 5.3 seconds was the time up. The time from liftoff to apogee was 23.18 seconds. The time, and we could add this stuff up. There should be something in here that gives you the total, and I'd have to look for it. But so we had 23.18 seconds from liftoff. We had the time under the drogue chute of 34.65 seconds, and the time under the main chute, 282.55. Yeah. Yeah. Next. Well, again, and I'm sure that actual time, I think, is where we are, was the total flight. So I don't think that was just under the main chute. But that gives you an idea that, yeah, we had a nice slow descent. And that's from that last 1,000 foot down. Next. So just showing you some of the fancy graphs and stuff. I can take a look at velocity, time to apogee, flight profile. Next. More talk about how violent my event was when I put out the drogue in the main, because again, you all of a sudden that rocket, put a chute out, it stops pretty fast. G-forces, acceleration. Next. So advanced telemetry systems. Right here, I have a substantially more advanced telemetry system. This goes in the rocket. This is called Kate. And not only does Kate produce all this data and downlink it, she talks to you. And we'll have to be very quiet because it unfortunately comes out very soft coming through the audio system, but we can actually hear what's happening with the rocket in real time. She's telling us what's going on. So we're going to listen to that. And this particular system is on a 900 frequency. Pretty crazy looking receiver and antenna. But I can also hook this up to a PC to get the information in real time. So go next. But that is a very, very pricey system, to say the least. And this is showing, again, this rocket that's going to go to 200,000 feet. These wires are just power wires. They're temporarily put on the antenna. So again, this is going to give us GPS and acceleration data, max velocity data, all that kind of good stuff in real time. And you can see right here, you see this? As you go higher, black powder charges don't work well. Now, you're going to say, well, wait a second, Dave. Black powder is an oxidizer and the fuel all in one. The reality is when you fire a black powder charge, the one grain is transmitting the heat from that grain to the next grain to cause it to ignite. The higher you go, the less air there is in between those grains, the less you have the heat transfer, and you get to very high altitudes, and the black powder really doesn't work well at all. Now, for some of my high altitude flights, I put a Band-Aid on it by taking that black powder charge and putting in a piece of surgical tubing and block that surgical tubing off. So the surgical tubing has a momentary expansion before it releases the pressure from those gases, which helps that problem, but it's not a solution. So in this case, instead of using black powder, he's using CO2 for deployment. And additionally there, he has some other interesting things. He has some Wi-Fi switches. This is a two-stage rocket, and we're going to talk about why this is important. So instead of using a mechanical switch to activate his electronics, he can use the Wi-Fi switches. Think about how truly important this is, because you don't want to be near this thing. For some reason, you put continuity to that charge in that upper stage, and you're standing close to the rocket or next to the rocket on a ladder, turning switches, and that motor ignites. That could be deadly. So the Wi-Fi switches give you the ability to arm things when you're standing away from the rocket. Some really pretty impressive work. Next. So let's be very, very quiet, and we're going to listen hopefully to a normal flight from Kate.
Hello, my name is Kate. I will be reporting GPS downlink information in real time during the flight. LCO, we are go. Please proceed with the launch.
That's coming from this.
1,000 feet, 3,000 feet, 6,000 feet, 9,000, 11,000, 13,000 feet, 15,000, 17,000, 19,000, 21,000, 23,000 feet, 25,000, 26,000, 27,000, 28,000. Max altitude 28,468 feet. Max velocity Mach 1.62. Peak acceleration was 12.6 Gs. Apogee was north-northwest at a distance of 0.62 miles. Descent rate indicates drogue parachute has successfully deployed. Now drifting north at 26 feet per second. 25,000 feet, descending at 110 feet per second. Distance 0.85 miles.
Now, I did edit this a little bit for brevity.
Excellent.
Descent rate indicates main parachute has successfully deployed. 500 descending at 26 feet per second. Distance 1.62 miles. Now at 250 feet. 100 feet. It has touched down. It landed at 28 feet per second. Distance 1.64 miles north-northwest at a compass bearing of 315 degrees. This completes my report.
Pretty impressive system. Everybody needs one of those. But I'm going to tell you why I don't like it. Next. So, yeah, you can see this is a pretty impressive rocket, and he's probably gone for over 200,000 feet. In the first problem I'll tell you about a project like this, keep in mind that probably from about the bottom up to about there is the motor. Long, thin motors are very challenging because you have such a long core that can build up a lot of pressure, and if it's not done just right, bad things can happen. And keep in mind that how much do you want to invest in equipment like this when bad things can happen? So let's take a look at how this flight went. Well, that looks great. Good start. Next. Oh, Houston, we may have a problem. Typically, black smoke is not a good sign. Next. Yeah, so you can see, yeah, so any expensive equipment you have like that is now part of this collection.
What did Kate say when that happened?
She wasn't speaking anymore.
So how much was it?
Oh my God. This is not my equipment. It's a friend of mine, so I didn't buy it. I want to say the receiver's like $1,300, and the airborne equipment's like $800 or $900. Where my trackers, like the egg timer mini I was showing you, the kit, $75. If I bury it, $75. And I spent some time when my wife wasn't home putting it together, but $75. Next. Yeah, that's not pretty. So one more. So I want you to, so we're not going to start this video just for a second, but I want you to watch this video very carefully, because one of the things that you're going to see, you're going to see some fuel grains coming down out of the sky, which I've had the pleasure of dodging burning fuel grains, which is kind of exciting. But one of the things that happens, the part of the rocket that does work, because I talked about that flight computer will put out a parachute even if things go bad, and it did. And it put out a parachute on this thing. This is just a fixed ground camera because nobody's crazy enough to be this close to this rocket when it takes off. But you'll see that what's left of the rocket comes down softly on the parachute and lands right in the fire so it can be burned up with everything else. And that, you're going to see that come out of this corner. So if Kate survived, she got burned, so go ahead and crank this up. Wait for it. Now watch it out right there. There it is. If you saw those fuel grains coming down burning, keep in mind that they're hollow core grains. They're burning from the inside out, and that's why you saw flame shooting out of both sides of the fuel grain. This is a friend of mine did this last year. I was out there when he was setting up. That's a two-stage rocket, and an N to an M went to 41,000 feet. It's pretty impressive. Next. My buddy Jim Jarvis from Austin. Here he's getting his two-stage rocket. You can see the upper stage starts right there. I'm trying to remember what motors he had in this, but they were big. He does a really good job with this. Next. There it is flying, and we're going to listen. Again, some of this is edited just for brevity, but you'll get an idea what Kate has to say about this. Go ahead.
Launch detected. 1,000 feet. 5,000 feet. Booster burnout 10,000 feet. 15,000. 20,000. 22,000 feet. 24,000. 26,000. Sustainer ignition. 133,000 feet. 136,000. 138,000 feet. 140,000. 141,000. 142,000. The apogee deployment charge has fired. Max altitude 142,148 feet. Max velocity Mach 3.66. Peak acceleration was 27.2 Gs. Apogee was east at a distance of 6.8 miles. 125,000 feet, descending at 1,000 feet per second, distance 8.2 miles. Now drifting 170 feet per second. Now drifting 19 feet per second. .500 feet, descending at 27 feet per second, distance 9.5 miles. It has touched down. It landed at 23 feet per second. Distance 9.5 miles east-southeast at a bearing of 103 degrees. This completes my report.
Okay, so any questions about that? Yeah, so one of the questions I normally get when we listen to this is, she said, drogue parachute has been deployed. Descent rate was like 1,000 feet per second. Well, wait a second, didn't the drogue deploy? There is no air up there. So she mentioned that, and the fact that it was drifting horizontally at 173 feet per second. And again, so I put this thing out, put the drogue chute out, but the rocket's still moving. It now has a horizontal velocity, and that's what you're listening to, because I hadn't had a chance to grab any air to slow it down. But it is nice that she gives us that information that, hey, that it did work.
So what frequency?
Yeah, so the question was, what frequency band are we using for 27 miles? Believe it or not, 900 works pretty well because of the altitude of the rocket. Okay. So actually, this is one of the better ones, because I'd have to dig through my old pictures. I actually have, where I've looked for a rocket, and I found a hole in the ground that has 3 vertical lines sticking her out in 120 degrees. So at least this one didn't make it all the way down. Somebody started to dig this out, but let's just hear what Kate has to say when things don't go well. But keep in mind, Kate's in the nose of this thing, which is now
Launch
probably...
detected. 1,000 feet. 10,000 feet. 20,000 feet. 25,000. 30,000. 32,000 feet. 34,000. 36,000. 37,000. 38,000. 39,000 feet. Max altitude 39,704 feet. Max velocity Mach 2.4. Peak acceleration was 36 Gs. Warning, warning, we may have a problem. Descent rate is too fast.
You don't want to hear that.
34,000 feet, descending at 610 feet per second, southwest at 1.41 miles. Warning, velocity is too high. 25,000 feet, descending at 880 feet per second, southwest at 1.52 miles. Velocity is still too high. Possible impact in 12.5 seconds. 10,000 descending at
She is.
990 feet per second.
It's not going to end well for her.
Southwest at 1.58 miles. Warning. Descent rate is too fast. Impact in. Correction. The impact velocity was 965 feet per second. Impact was 1.58 miles south-southwest at a compass bearing of 199 degrees.
So
This completes my report.
that's the receiver taking the last data point and interpreting what happened. Kate's didn't make it, I'm sorry to say. And that's why I like putting my less expensive devices in the nose of my rockets. Next. So just kind of an interesting rocket. This was a, you can see it being loaded. This is powered with how many newtons? This is like a 65,000 Newton second P motor. This was supposed to go to 60,000 feet. Next. This is what I was talking about before with the Wi-Fi switches. So in this case, he's turning Kate on, but again, without any staging in it, without the igniter in the bottom of the rocket yet. It's a reasonably safe place to be. But you don't want to be standing at the top of the launch rail like that, arming a two-stage rocket, and that's why the Wi-Fi switches are important. Next. And you can see this one has like a reddish flame. It's not like the others. He spit the nozzle at about 20 some odd thousand, or about 15,000 feet. So he only got about 35,000 feet. Next. This is kind of fun. It went to Mach 2.6, and what you see on that rocket is what we call Mach crash. Took the paint off the rocket. Next. And this is what we get. That's that more complex live telemetry you get that's giving you this picture live right on Google Maps as your rocket is flying, which is really kind of nice. Next. So my rocketry goes in a little bit different direction than everybody else's. Any aviation history buffs here? So this is a scale model of the Bell X-2, and that's an interesting story in its own right. That's powered with a K-class rocket motor, about 2,600 Newton seconds, the equivalent of 260 C motors all going off at the same time, via radio control. Next. You can see there's a picture of it in flight. Great, and I'll have some video of this if we have time left. Next. In that model, kind of circulated around the rocketry community, and I get this phone call from this guy, George Walsh, who's the curator of the Flight Test Museum at Edwards Air Force Base. And to make a long story short, it's now on display at Edwards Air Force Base between the X4 and the M2 F2 lifting body. The gal between us, the guy on the far left here is Mike Ozer, a friend of mine from the North Dallas Radio Control Club. And he is, I believe, a member, or at least was a member of the Falcons of Lake Dallas. He did a lot of the CAD work and picked the airfoils and did a lot of the design work for me on this thing. It was a year in research, development, and design, and 2 years putting that thing together. And the gal in the center is Lori Abt. The last person to fly the X-2 and the second person to get killed in the X-2 was a gentleman by the name of Mel Abt, who went to Mach 3.21. And shortly after that, he started a turn, lost control of the X-2. He got killed. To make a very long story short, his daughter was 5 at the time. This is at the Flight Test Museum, the 60-year anniversary of that, 60 years later. And there she is. And her mom and she left Edwards when she was 5 years old. Her mom never retired or remarried. They never returned. And here she finally returned 60 years later to see my model on display because there are no more X-2s. They both got destroyed. It was kind of a very, very special moment. Next. So just a couple things here. You may all want to get a picture of this. Interested in RC flying? Falcons of Lake Dallas RC Club. George and I are members of that. Great place to fly. National organizations below that. Our local high-power rocketry club is Tripoli, North Texas. There's the website for that and the website for the national organization. Okay.
Clear sky.
So that's that Bell X-2.
This rocket is flying in 5, 4, 3, 2, 1. Ignition.
So he's using a telephoto lens to zoom in on this thing. Model is 8.5 foot long, 46 pounds at takeoff. About 3.5 pounds of propellant.
Come on, do a loop, Jay. You will.
That's a K470 motor.
A K470 motor.
I'm flying it. 2 years building this thing, I'm flying it. Now, the nice thing about flying about Black Rock, part of the lake bed we're in is 17 miles wide and 23 miles long. I have a 23-mile long runway for this thing. Perfectly flat. Yeah, so it was powered for 5.3 seconds during the boost, and now it's all glide. Actually, well, and that's the way the full-size X2. The full-size X2 was rocket-powered, and it did its thing and came gliding back. And if you've ever seen the newsreels from the 1956, God, they look just like that.
Very well done.
So just a couple slow motion clips. 185 miles an hour on the vertical. And one thing about this, you know, flying a radio control model, if it's flying too fast or I don't like what it's doing, I can chop the throttle and land. With this, once that motor lights, I'm along for the ride. So that's the boost in slow motion. In the X2, my model, like the full-size X2, didn't have landing gear doors like a jetliner or a jet aircraft does. It actually had a hatch that got blown off and then the nose gear comes down. In my model emulates that. So you'll see the hatch separate from there. That's the hatch floating away for the nose gear. And the nose gear comes down and locks. And again, just like the newsreels in the 1950s. I flew it twice. It was the third flight I was getting ready to go when I got the phone call from George Welsh, who begged me not to fly it. And he said, come on out to Edwards, or we got a $6,000 budget to get this thing shipped to Edwards. And I said, well, it doesn't matter what your budget is. If it shows up on your doorstep banged up, that's not going to do us any good. So he said, well, I said, I can bring it out. Believe it or not, going from here to Edwards, then up to Black Rock is only 123-mile deviation. So he said, you come on out and we'll make a day of it. I said, I'll be there at noon. He said, no, you need to be here at 8 o'clock in the morning. And we had just a great time out there. I mean, they really treated us. So let's close this and go to the next movie.
Dave, I have a question.
Sure.
Did you have any kind of stabilization in that thing?
Oh, pause the next movie. That's a great question. Did everybody hear that? Do I have any kind of stabilization in the thing? So I was using what's called an Eagle Tree Guardian, which is a really cool device. So it has three modes. It has completely off, which means it doesn't do anything for me. It has what they call 2D. And in 2D, what would happen is if I put it in that mode and the aircraft was banked or inverted, it would automatically roll it upright. And it has 3D mode, in which case, when I enter a bank, like if I enter a 45-degree bank and I let it go, it's going to hold that bank for me during the turn. Now, the system is capable in all axes, but because a glider has to seek its own attitude, I had it in roll only, and I used it in the 3D mode. And what that did for me is it meant that my roll trim was perfect during the flight, because any minor misalignments we may have had during the building process would have been eliminated. So that worked out real well. So that's a great question. And I did use it in the 3D mode. In the other thing, if I lost sight of it, if I got behind the smoke, which I've done with some of my rocket gliders, I could flick it to the 2D mode, take my hands off the transmitter, and somewhere in that 23-mile length of playa we had out there, it would land all by itself. So next, go ahead and do that one. Keep in mind that the blue section's the rocket itself. In slow motion, and I want to talk about this momentarily. So after that happened is when I started dodging fuel grains that were coming out of there. So the question was asked before, do we do anything important with the telemetry that we get down? So what actually happened on that flight is the fuel grain during the burn, parts of the fuel grain came apart and momentary clogged the nozzle, causing the motor to overpressure, and you saw the result of that. That was determined by the telemetry that we received and a close examination of the video of what happened. So we were able to corroborate what happened, because what the telemetry showed was just before the rocket blew, there was a deceleration event. And the deceleration event happened as the nozzle clogged. And if we didn't have that telemetry, he wouldn't really know what the problem was and how to fix it for the next flight. So that's a great example of the value of having that telemetry live. If he didn't have the live telemetry and used the equipment that I'm using, that information would have been destroyed with a rocket, and he wouldn't have that information. Yes, sir.
Did you say he built that motor?
He designed and built that motor. So there are those of us that are using pre-manufactured fuel grains to build up our own motors, or pre-built motors, but a lot of people will make their own motors. So, and that's a whole hobby onto its own. Yes, sir.
Do you ever contact colleges and get your master's students or PhD students to get involved with you to collect and do research?
So that's the question was, do we work with colleges and schools to do research? And the answer is absolutely. There are two things that I'm a big participant of. The first is an event called TARC, which is for high school students, which they have to launch 2 eggs, and they have to go so high and put the flight up for so long. And that involves about 850, 900 schools each year. Top 100 go to DC for that competition, so we do that. The other thing that we do is Spaceport Cup. And Spaceport Cup attracts colleges from literally all over the world. And they go out to New Mexico, the spaceport out in New Mexico, and they fly rockets. They have 2 events, one to 10,000 feet, one to 35,000 feet, in different classes of motors. And we work with a lot of college students doing that. I would say if you come out to one of the Tripoli, North Texas launches in Seymour, about a third of the large rocket projects you see flying are not modelers. They're university projects and groups doing that. And you see some interesting big projects fly there. And being that these kids, some of them hadn't had any rocketry experience at all, they don't always go as planned. But we, they have to be inspected by us to make sure that they're not going to have anything that's going to create a safety issue. Okay, there's one more video. Let's check that out. But you can see the value of live telemetry. And what happens is in that particular motor, in large motors, a lot of the times when well, I'll let this run and then I'll talk about that for a second. So you're going to see just a close slow-mo or a close-up of the launch itself, but then we'll jump to what it looks like sitting in the cockpit of this thing.
This rocket is flying in 5, 4, 3, 2, 1, ignition.
No good launch is not any good without some slow-mo. So now you get to see what it looks like inside the cockpit. By the way, this video was taken in September. It'll be the 10-year anniversary of the flight of this thing.
Is this flight number 2?
This is flight number 2. So while you're watching it set up, the first time I flew it, it was interesting. It was kind of a cloudy, overcast, breezy day. We had some storms. And I flew it when it was overcast, which actually kind of, for me, worked out very good because I wasn't going to go into the clouds. The second time we flew it, it was crystal clear and beautiful, which is one of the reasons I agreed to let the Flight Test Museum have it, because I couldn't possibly get better pictures and video than I got on this flight. So there it is during boost. And when it leans over, you're going to see the expanse of the Black Rock Desert. That is 100% perfectly flat. You can drive 100 miles an hour from one side of that to the other. Yeah, I did. Looking at the cockpit of this thing kind of reminds me of that first scene in the Planet of the Apes movie where the ship's maneuvering. Listen for it. The gear just came down, that's why you got the change in noise. All right. So the question, going back to the Discovery Channel question. So what you've seen here is just a very small smattering of the stuff that I've done. Years ago with a bunch of my friends, we built a 10-foot long, 5-foot across X-30, which was the National Aerospace plane. It was supposed to go from the West Coast to Tokyo in like 30 minutes or something like that. NASA never got the thing to fly, so we built our model and we actually had 3 flights on it. The last flight was captured by the Discovery Channel, and we were out in Argonia, Kansas, and that was before the crazy redheaded girl started doing her thing. They had a nice thing about our LDRS launch. LDRS standing for Large and Dangerous Rocket Ships. That's what LDRS stands for. And we took it out there and we flew it. And I had somebody came in town and watched us work on this thing for several hours. And then when I went up on Argonia, we actually had a photographer following us around, taking pictures and interviewing me for 3 days. So it was really kind of interesting. And that was before things really kind of fell apart with their crazy stuff that they decided to do, but yes. All right, I'll let you all finish up the meeting. If after the meeting you want to see some of the installation here, what I have for a tracker, I do have some questions for somebody who's really sharp on fox hunting on some issues that I'm having trying to find my beacons. And gentlemen, I appreciate your patience and hopefully we had a little fun tonight.